Good morning and welcome everyone. I am really glad to see, well, the numbers are climbing and we've got such good representations from various schools. So thank you all for engaging with us in the chat box this morning. Today, I am joined by Dr. Sophie Marquez from Stellenbosch University. So hi, Sophie, how are you doing?
Hello. Hello, I'm Sophie. I'm doing well. Thank you. And nice to see you all. And I hope you have fun today with us.
So today's aim is to essentially engage in a discussion about abstract algebra to understand what we mean by abstraction and how can one utilize mathematics to understand everything around us. How can we utilize it to perhaps model and, well, what other words am I looking for, Sophie? Perhaps a deeper understanding around us?
Maybe, yes. And also how maybe we can think about how we speak to each other and what we are doing without noticing. And math helps us to formalize this, and maybe at the end of today you will know how to communicate better or how to think better of what you say and how you say it.
Perfect. I fully agree. So today we look forward to engaging with you, and what we would like to say from Sophie and myself is that we would like for you to make full use of the chat box, use the raise hand function. Please interact with us, provide us with some examples. If you don't understand something, also let us know. If you provide an example and we tweak it or we find a mistake, it's perfectly fine. So let's learn together and let's have fun today. That's the aim. All right, so perhaps I'm going to hand over to Sophie, because Sophie, the first question that I have is, what do we mean when we talk about things that are abstract? What does the word abstract mean?
Well, I will return the question back to maybe some people which are in the audience. What do you think abstract means? Would you be able to tell us what are your intuitive, or maybe you already know the definition, but maybe the definition is not unique, but what abstract means to you? It would be good to hear from you.
Yeah, please engage in the chat box, but maybe if I can start, Sophie. For me, I feel something is abstract if I cannot perhaps see it. Am I on the right track?
Is there a right track? Maybe there is, but yeah, maybe I can relate to that. But it is maybe what we think. But is there anyone who would like to join in and speak? If not, it's okay. But it would be good to have an idea of what do you think about abstraction yourself.
Yeah, please feel free to raise your hand and we will permit you to unmute. Otherwise, please make use of the chat box.
So, anyone? I see we have people coming from. Okay, I see something that is non-representational. Atini, would you like to elaborate on that? Would you like to have the opportunity to speak?
Yeah, let's give Atini an opportunity to speak. Let's see. Hi, Atini, how are you? Maybe there's a problem with the microphone. But yes, so Atini says something non-representational. So essentially, what's being said is that I feel like what's being said is that I cannot represent this
in a maybe concrete way.
Yeah.
So someone is saying that if my device is not functioning well, but I'm having difficulty with a sound. The volume is very low. Is there anyone else who has this problem right now?
I think it might just be Tumelo because we're getting other responses in the chat box, which means that students can hear us. Tumelo, we hope you resolve it. But let's look at the responses.
There is Paulus, who has his hand up for quite a while. Maybe we can give him.
Absolutely. Paulus, please go ahead. But looking at the chats, if I look at the responses here, someone says, well, Peter says, abstract may mean representation of something unusual. So Sophie, if I have, okay, so maybe we also have to look at what is unusual, but even if it's something ordinary that everybody could find in their real everyday life, would I be able to talk about such a common thing abstractly?
We could probably try to see if abstract could be seen that way as well, because at the moment, all the answer does not have physical existence, does not exist physically. So it seemed to be a common trend. But how about if I ask you about what phone, or how do you think about, how could you describe your phone?
Yeah, maybe can I comment, Sophie? Because for me now, from the responses and from the hint you kind of gave me, I feel like maybe abstract means it's something that I cannot touch, feel, and see, you know, something like that. And then if I'm talking about phones, are you now referring to the fact that if I have a phone and you have a phone and I call you, that call is allowed to take place because there's some invisible signal going from my phone to your phone?
I'm not referring to that, but maybe in the way we speak about our device, we are abstracting something out of it, because so it would be a different abstract where we take something very concrete and we remove some information about it to describe it. So that kind of abstract. So but then, maybe someone might not see as clearly as does not exist, or it would be a different dimension maybe, or a different way of abstracting.
So so basically what I understand is that we now need to perhaps look at quite a few cell phones and pick out some commonality amongst them. Is that what we're doing?
Somehow, yes.
Okay. So yeah.
So what would you tell me? Tell you, ask you, what is a phone? What would you tell that someone?
Okay, to me, a phone is a device that allows me to communicate.
Okay.
I can make a phone call, or I can send a message.
So you never use a calculator on your iPhone?
I could use it, yeah. Well, I don't have an iPhone. I'm using a Samsung. Okay. Does that make a difference?
I don't know. Maybe. You use your calculator, Atini? I think a few of you use. And so the brand of your phone might be something that you would use to describe your phone, like, but that kind of, and then by saying the brand, maybe you can visualize already your phone, on what kind of phone it is, and represent it in your head. So you would basically abstract your phone to a brand and already have an idea of the entirety of your phone, where you have forgotten a few functions that you might not use. So depending on what you do with your phone, you might describe it in different ways, if that makes sense.
Okay, so maybe I just use my phone to check the time.
Exactly. That might be your main function. So your phone is your clock, and you might see your phone as a clock.
Okay.
But it's much more than that. So when you think about anything, you are kind of abstracting the main functionality of that thing in order to find, as you said, commonality between them, in order to be understood by others.
I see. So are there any other examples that perhaps the students could think about, apart from cell phones? Is there any other collection that we could consider and then talk about properties of it? Because that's what I'm getting from this, Sophie, that we need to consider a specific object or type of objects, and then I am extracting properties of the object. Isn't that so?
That could be a form of abstracting to me, at least, where the object lose a bit of its concreteness and it's described through some property, more like abstract, far out. But it could be something more, but we can speak about it later. But let's see, what kind of abstraction would you come up with? We would be very interested to hear about it.
So the first example that we just encountered was considering cell phones, where the abstraction was done at the level of brands of the phone. Isn't that so?
That could be one, or you also like you could also see it as a brand, or just something to communicate and forget about any other functionalities that you might have. So you abstracted some property of your phone. So anyone else wants to try to see abstraction of some kind, something that you like a lot, and abstract and realize that you are forgetting about a lot of functionality of your thing.
Mm-hmm.
No one?
I'm trying to think.
Your laptop. So how would you abstract your laptop, Patini?
Yeah, maybe my laptop is a device for which I use to type up documents.
Mm-hmm. But for someone else, it could be a device where they play video games the most.
Agreed. Yeah.
So it could be a video game for them. They would only abstract that functionality and abstract the property which matter. I think the important thing, a book.
Mm-hmm.
So I'm using my laptop to Zoom and Netflix. So you have only two functionality, but your laptop is much more than that. But imagine if you see your laptop as a laptop technician, your laptop technician will think of a laptop very much differently from you as a user, because you would see more it concretely as component and as how everything what is your RAM, what is your battery shape, or a lot of different way you will see the same object, but depending on what you do with your object, you would abstract it in a different way.
So the abstraction seems to be dependent on the user or the person that is now making the conclusions.
I would believe that something which is abstract for someone could be very concrete for someone else. Also, I think that what we might not be able to agree all on what is abstract and what is concrete. I can say that something is very abstract to me and someone might tell me, but no, that's kind of non-abstract at all.
I see. So it's very relative to the person, in a sense, or the situation that you're in. And it's all about, as we say, reducing the object, perhaps, to a specific property. So me focusing, as you said here, extract or remove something. And that is what we want to do when we abstract, right? Or when we perform this method of abstraction. Is that correct?
Yes. I think there is a very good comment of Leila also. Say a divide by someone used to type up document also apply to other objects such as a typewriter or a phone. Should we try to abstract quality that are unique to a specific object? I think she's right on the point here, because it depends very much on what do you want to do, right? Because depending on what would you do with that abstraction? Maybe you do abstraction, but you don't even realize, but it would be part of a conversation where you're abstracting some things because that's what mattered in your conversation. But if you want to, if for instance, it's someone who is foreign, a foreigner, and want to try to understand what is an object and he does not know the name, you will want to give him more and more detail until he reached to the point to exactly know what device you are speaking about. So if you say that's used to type document, then he might have a set of objects in front of him that he can consider, and then you will say, oh, but you can also watch Netflix with it and all, and then you will have less device, and at some point you will understand that it's a laptop. So it will be very so there is another person who wrote a comment, are we not supposed to be doing algebra? We are, very strangely, but this is algebra. It's like the basic of algebra.
We're getting there. Okay, so I can also, based on this discussion, Sophie, essentially say that it's a type of generalization, isn't that so?
In a sense, I would say. I think we need to be aware of the word. Maybe we can, some of us can use them interchangeably, but maybe maybe the process of generalization is more, in my head, opposite process, where you take one individual and you generalize it into more, but while here you take a lot of things and you are trying to find commonality on those things, removing some of the content.
Yeah, because what I liked when you were just talking a moment ago was the fact that these properties that we removed or that we ascribed, those properties can help someone determine which object you are talking about, right? So it was kind of reverse abstraction in a sense, right?
Yeah.
But yeah. So this is what we now formally have as a definition for abstraction. So what is abstraction? Well, it is merely the act of removing a characteristic to reveal a commonality. And that is why we were using these words, finding the commonality amongst, an object, for example. And in particular, when we were talking about cell phones, well, one commonality would have been all phones that are branded as, for example, Oppo, or another commonality would be the brand, let's say, an iPhone. So the commonality that we shared in that discussion, in that example about phones, was branding. That is what we did. But we also spoke about other things, other properties. For example, I said I use my phone for making calls as well as messages. Then there were examples in the chat box where we said, well, if you've got a laptop, oh, Sophie says, you know what, perhaps she uses it just to play games, or she uses another device just to watch Netflix. It was something like that. So these are the commonalities, that the properties that we are talking about that are being extracted when we refer to a collection of objects, for example, just looking at phones or just looking at laptops, etc. But it seems that, Sophie, in order for us to talk about this abstraction, in order for us to refer to the commonalities and these objects, we have to have some type of formalization, some type of language. So how do I go about doing this?
And I think that's also a link back to the question of Tendo, who is in the chat, who said, does it mean that we continue to name quality that define an object? So it means that you are trying to kind of formalize your object in a very specific way that will make sense for most of us and that we will all understand. And that's what we do in abstract algebra. And Yolandi also say, is abstract algebra going to be different from regular algebra? So if your regular algebra is just it's counting and solving equation, yes, it will be, because it will be more abstract than just doing computation. And it will be all about formalizing things, defining things, creating a world which we apply logic. So can we abstract real part from complex number? That's another type of abstraction where you kind of remove the imaginary part from the real number. So it could be seen as an abstraction where you kind of remove some information from your complex number. But yes, I think one of the part, what you said is very correct, is one of the part would be to formalize in some way where you lose information. But I feel that when you have too much information, it's difficult to keep track of things. So if you only take essential information, there is a way to communicate with each other in a much more efficient way, which is what we do in mathematics in somehow.
So how would I do that? Where do I start? So how do I represent, for example, the object or the property of the object?
Maybe we can see, for instance, with the next slide with the Earth, where it's not really kind of, but it's telling you that you need to find a way to express yourself, but not too abstract, because if you are too abstract, nobody understands you. If I do a square with a line in the middle, you won't understand, even if it's red, you won't understand that it's hard.
Yeah, I wouldn't. Yeah.
But everyone understands that the middle part is the Earth. It's like a very common language that we use. So it's a form of abstraction, but you would need to find the right place where you lose information, but you're okay to lose that information for what you are going to do with it later.
Okay, I think I'm, right now getting a better understanding about this. So we also have to be very careful on how we choose to represent, well, not really represent, but perhaps the properties that I'm going to select about the object, isn't that so? That will then represent it.
Exactly.
Yes, because it seems like, yes, using the square is not providing enough information for someone to ascertain that this was something about a heart. But using the representation of a heart does have adequate information recorded for it. So I hope everybody is understanding this. So we have to be careful about what information we select when trying to perform the abstraction.
Yes, but for instance, the Earth, like the one in the middle, might not be something that it can still mean a lot of things. It could be means like emotion, like love or whatever. It could mean the Earth, like the real organ, but that type of abstraction might not be the best in every single context. So you're just right. Depend on the context you are in.
Okay, so in particular, you're saying that a surgeon is not going to be happy with our drawing of a heart.
No, not at all. I don't think that Earth will help him to do a surgery, unfortunately. Okay. I wouldn't go to a surgeon who has a vision of the art like that.
Agreed. Okay. Yeah. And
So,
here we have.
Yeah, here is the same thing. No.
Yes, I wouldn't be able to tell from the yellow Lego that that was a duck.
Me neither. That's a bit too abstract for me.
Yeah.
Maybe if it was agreed with a lot of things, a lot of people that was a duck, maybe it would have been doable, but I think it's way too little information. So we have Lebogan who is saying, so abstract mathematics will be about replacing or substituting a non-existent number from a real number. I wouldn't say that. I would say that maybe the next slide would help. I don't remember what is, no, it's the next one, because this we already spoke to it. So here a very common abstraction that we are doing. I don't know if you will get it, what I'm trying to come across with that, but this is the idea of a number. A number is I think it's a very good abstract notion because it's at the same time not real, and at the same time it's abstracting an idea from something real. But it's not real because if I tell you what is one, you would not be able to show me a one. Like you won't be able to come up and show me a one which represents all the one of the universe. You will tell me, yes, there is one chair here, there is one table, but one in itself is a very abstract concept. So how do you learn what is one? You learn it by understanding a concept, by thinking about, by seeing a lot of the same pattern out there. And we will tell you this is one table. You understand the concept of one table. You can understand the concept of one chair. You understand the concept of one ball. And at the end, you will understand what one is, even though you cannot represent it concretely. So that's, for instance, what algebra does, is to kind of really concentrate on those very, very abstract notion that you might not be even able to represent physically.
So in this comic, what we have is we have different objects essentially representing the same thing, right?
Yes.
So at the bottom, right here, I've got one bird, followed by two birds, followed by three. And so what is happening in each of the following pictures is the same thing. It's about assigning a number to each of these things, isn't that so? It's one tree, two trees, three trees.
Exactly. And that's what happened in your mind. where you start making a connection between the object itself does not matter, but there is kind of a concept which is attached to it, which is how many of that object can I see? And it's very difficult to formalize that concept because it's very abstract, but we all understand what is 1 and 2 and 3.
That's really nice. Do we have any questions so far? Atini says too abstract. Okay. Yeah, but that is the essence of this comic. So here we're counting how many of these objects belong in each of those sections. So here there are, in particular, 2 knots, or maybe we're not counting knots, we're counting the, what are we counting here? So
yeah, that's another thing, is like to decide what you are counting is very important, especially if you are learning numbers, maybe and you're in foundation phase, you might see things a bit differently if the question is not asked in the right way. But if we just count how many rope there is, then there is 1, 2.
yes, because this is 1 row. There's 2 in here, 2 segments.
That's also 1 rope and 1 rope. But if there is a node, then it will be 2, 3, and 4. So it depends on what you are counting.
Okay, that's also interesting. And then, of course, the last one is dealing with blocks. But this one, again, I think one square, 2 squares, 3 squares, right?
Yeah.
All right. So we hope everybody is understanding what we were trying to communicate about abstraction. So the object may not necessarily matter, but it is the properties that we're trying to ascribe to it that does, right? Is it fine if I move on, Sophie?
Mm-hmm.
Okay. So this one's about sets. So why do I need sets?
So I guess we are surrounded of sets, right? Everything is kind of a set. We are very good at making sets, I feel. Like, in a sense, every single word we utilize corresponds to a set in our head. If I use the word tree, again, like in the same way of the previous slide, I can have in my head all the trees that I have seen in my life, but they are kind of forming a set of all the tree. The color, I can have in my head all the things of the same color that I have seen in my life. So the concept of sets is brought in math to kind of formalize that thing that we are doing in building set around us. For instance, if we say do the set of women and set of men, set of children, or set of adults. So we could do plenty of sets.
So the set, well, sets mathematically, which is what we're defining now, this is going to help us represent the abstraction, is it?
In a sense, we could build a set out of a commonality that we have seen among objects and abstracted from the object.
So I'm going to use sets to actually describe the objects I'm looking at. So I have to start with the objects first.
I would say it's difficult to know sometimes what you do first. There is this thing of the egg or the chicken all the time, because you could just, someone else could just come and bring you a bunch of objects in front of you, and they could have absolutely no relation for yourself, and they are still a set. So the object could have absolutely no relationship and still form a set.
Okay, let's talk about some examples now, because I want to understand this properly. So you're saying I can consider anything that's around me and it forms a set. So right now I have a pen. I'm not sure if you can see it. I also have a book. Does this form a set?
Yeah, you could form a set of a pen and a book.
Okay. Are there any other examples that you would like to share in the chat box, perhaps? We'd like some participation. Please let us know. What sets would you like to talk about? So what we understand is that essentially a set is a collection of things, right?
Yes. You'll only say that, for instance, the set built on the interval notation. Yes, you could have. That set is even infinite, like all the number which are in this interval. So that set is maybe abstract to some, maybe concrete to others. So from the pen you are carrying, we have a set of black and white color. That's quite cool. I like that one.
That is nice. Yeah.
The colors of the set, yeah. The collection of cutlery, that's also good. You could have a set where you have, but you see, in order to describe this, what I can notice out of those examples is when we have to describe a set, they need to be kind of description that we can do.
Okay.
So in the set which are proposed, there is kind of commonality between the thing. If we would like to describe a set where there is absolutely no commonality, at least that we can see at first, we would have to list all the elements individually. For instance, I would say there is a set of one cloud, a set of one flower, a set which has one cloud, one flower, some water,
Okay.
a leaf, but I couldn't find maybe some commonality out of those, so I would have to list them. So that's why probably the set that we are getting in the chat box, it's easier when there is some commonality and that we can do a collection of some common thing, but we don't have to. We could put very random thing together.
So how does one denote these sets? Because now we have described them. You just said, you know what, a cloud, a flower, put them into a set. But how does one mathematically perhaps, formally write that down?
So usually in mathematics, we like to give names to things like we do in English as well. But mathematicians are quite trying to be simple, even if we look complicated in the other end. So our names are very short. So for instance, we would call our set A, a big A. So we give it a name. And then we put an equal to say that it would be equal to what we put in the other side.
Oh, but now how do I formally write down the other side?
So you would open accolade.
Is round fine?
No, because the notation is very important. So it really needs to be an accolade.
Okay. So that?
So that symbol in English, you would write it as what A will be the set with whatever I put inside.
The cloud, the flower. Okay, my flower is not going to be great, but here we go. and let's say a heart.
That's it. That's very well a set.
Okay. So is this fine? Is this a set? Can I denote it like this? I mean, is that fine?
Yeah, that's a set. That's exactly how we write the set of those three objects. So I see that Le Bogan has a set. Maybe he wrote the set of I guess, all even number. That's what you came on. So the only problem is that if you want to write a set, you cannot put those round brackets around it. You would need to put accolade for the notation of sets. Otherwise, it's not, it might be understood as a n tuple instead of a.
Maybe I write the set of E, I can just denote it by E, right?
Yeah.
And then you said equality. And then I have to be very specific with that bracket, the curly brackets that you call the accolade.
Mm-hmm.
And then now the example was even numbers.
Yeah,
okay.
It's 2, 4, but Libogan already wrote it correctly in the chat, but you can write it for everyone. You already got it. So well done.
Is 0 not there?
Yeah, because you wrote only from 2.
Okay, we'll use that one, right?
Because he didn't wrote all the even number, indeed. It just started from 2 and then. So I don't know if he meant all the even number starting from 2.
Okay, all even numbers starting from 2. And so that's how we write that mathematically, but this is just all even. Can you see? From 2. Or greater than or greater than 2, I should say.
Yeah, maybe it's more. So Tendo say your set does not have to have object or number that share common ground. Are you simply listing in a mathematical manner? Yeah. So your set could be whatever. It's still a set. It's called a set. But it will happen very often that indeed the set that we use might have some common ground, because it will be easier to use a set where you can find some commonality within the element in order to describe something more precisely. But use a set where you know nothing about your set and every single object is very distinct, it will make it a bit harder to use that set. So sometimes you will use set which have some commonality, sometimes there is no commonality. But it's harder to deal with those without commonality of description, which is kind of systematic. But you could do set with anything you like, really.
Okay, so I think maybe the next thing is, now that I know how to formulate sets and I understand that sets can literally be collections of anything. Yeah, so that means that this is allowed, right?
Yes, it is. Just 1 minute, Serene. Kayla is saying that in the whiteboard, would you be able to open the whiteboard again?
Sure. Here we go.
Thank you. So she just say, instead of greater than 2, should it be greater or equal to 2? Greater than or equal to 2. So here, I guess it depends on the how you define greater than. If you include in your language that equal is included in the greater than or not. But if you don't, then you would have to add greater or equal to 2. So Tumelo is asking, is a set different from a pattern? It is, because a pattern will be like a list, kind of a list of things that you are observing, and you are trying to find a pattern out of it, or there is some kind of commonality out of it that you will take into consideration. Now I'm trying to, but you could put in a set a list of things which come from a pattern. You are allowed to do that as well. So set is quite a very large notion. You can do a lot with set. You can put everything you like in sets. Thank you, Siri.
Okay, but should we perhaps comment on how this set can be described with the pattern?
We can. How would you describe a set that Lebogan described? Would you be able to describe it with a pattern?
Yeah.
Anyone? Maybe Lebogan, you would be able to describe your own set with a pattern? It is only a pattern if it is repeated. So maybe we need to kind of agree with the definition of what do we call a pattern. So what is a pattern? So would you be able, who spoke about patterns? Tumelo, what do you mean by pattern in your question?
They said arithmetic number pattern.
So what, but still a bit abstract, isn't it?
Yeah, yeah.
So would you be able to, a group of objects that are repeated? So what do you mean by repeated? Would you mean like 2, 2, 2, 2, 2? Would that be what you mean by repeated? So Tendo say, can a pattern be numbers but share some common, like we can predict the next number using a common value? Something like that. Tumelos would say, I think I would describe a pattern as a set of number or objects that increase or decrease in a certain additive or multiplicative common factor. So each of you have a very specific notion of pattern in it, because you see what you are doing. You are looking at those patterns that you have observed during your life, and you are trying to abstract a definition out of those observations that you have made. That's what I'm feeling that you are doing right now. So you are trying to abstract the pattern you have observed, and how are you trying to define them right now? So, but it's still very specific to the context you might have observed them before. So for instance, the pattern that Ursula mentioned would be maybe a pattern which will be used in knitting, for instance. You are knitting a pattern and then you are repeating that pattern again and again and again.
Okay.
So that one way I could see that the pattern using that definition come across. And the other pattern that I have seen, so we have another one, Bismarck would say a pattern is a function whose domain is a set of natural number. So this is very also specific to natural number. Tenda, sorry for that. Pattern are a set of numbers that are determined by a certain common difference. So we all have a certain idea of what is a pattern. It seems that you see that this is what I told you at the beginning. I hope that you will use the lesson of today to maybe improve your communication, because in this little lapse of time, we have agreed that we all see words in different ways. And when we communicate, we don't always take in consideration this fact that the word we use might mean different things depending on who we are and our own experience. And that could result on some fight or some misunderstanding or something like that. So keep that in mind, that you might have a very strong idea of what a pattern is, but it does not mean that someone else who has a very strong idea of what pattern is wrong. It might be that there are different ways to approach the concept of pattern. And that's also what is abstraction doing, is that you don't realize that you are abstracting from your experience a definition of a pattern, but you cannot for sure say that's the definition, universal definition that everyone will have at some given time.
So by asking this question, what we've actually engaged in is abstraction, isn't that so?
Say again.
By asking this question about how can one rewrite this or represent this pattern, we have now engaged in abstraction.
Exactly. It is. So abstraction is everywhere, really. We always abstract something. So Ursula is saying somebody asked if a set is also a pattern. A pattern can be a group of objects that are repeated, usually in the same sequence. Ursula, can you give us, for instance, what would be a set of pattern for you? Or can you write us down a pattern that you would have in your mind? If your pattern allows you, your notion of pattern allows you to write numbers. You could do a set of numbers, it's the easiest to type, I guess. So could you give us an example of what it will look like if you wrote a pattern as number, as a set of numbers? Okay, so she wrote triangle, circle, triangle, circle. So it would be like more a sequence of things that are repeated.
Okay.
The pattern. So you see that your pattern, Ursula, and Le Bogan pattern seem to be like slightly different. We might find commonality between the two, but Le Bogan say 5, 10, 15, 20 is the pattern. And now Bishmore is asking, but what is the difference between a pattern and a sequence? So could you, Ursula, put a sequence of there? Did you put a pattern again? So Ursula, could you put something which is for you a sequence, but not a pattern down? P6, okay. So that's again a pattern. So there is a lot of different, I will tell you also over example of pattern. I haven't seen the definition of pattern, but includes exponent yet. X squared equal to Y is a valid pattern. That's what Leila say. And then there say 3, 9, 27, 81 is a pattern. And Raquel say 3, 6. So 3, 9, 27, 81. And then Raquel say 3, 6, 9, 12. And 15. So and Ursula gave another pattern where she say 1, 3, 5, 7, 1, 3, 5, 7. So it would be of the same type of the first one, 1, 3, 5, 7, 1, 3, 5, 7. And Tinon.
Maybe I should have these commas here, should I?
Yes, she put commas everywhere, and then she put how do you?
Semicolon.
Yeah, semicolon in between.
I think maybe we have quite a few
know,
responses here, right?
yeah, I would just maybe read out the other one just because there is an over 2, 4, 16, 256, which are powers of we can also reflect on that, but and then the sort of pattern will be 2, 4, 6, 8, 10, and 3, 6, 8, 9, 12, 5, 10. So Tumelo has a very concrete idea of what the pattern is in what a pattern should be, but maybe your notion of pattern is a bit too restrictive in some sense. And what is the meaning of Raquel? I don't understand why you put a at. Maybe you can
I
explain.
think it was referring to somebody else's response. It's the x squared. It's about exponentiation.
Ah, okay. It means x squared. Okay, thank you. So the x squared means x times x. So x at 2 means x times x. A set is not always a pattern. A set can be defined. A pattern can be defined. And then 1, 1, 2, 3, 5, 8, 13. You can add the first 2 number and get the next. That's another pattern. Okay. So we have a lot of example of pattern, but now what Serene was asking is if we take the first of all the pattern we considered, which is 2, 4, 6, what can you say? If we wanted to really, because I cannot keep listing all the elements all the time, because otherwise we can stay here until the end of time, right?
Yeah.
That will not be possible. But how would you be able to describe efficiently every element of that set? So, for instance, what is 2? What is 4? What is 6?
Positive numbers?
It's positive, yes, but it's more than that. So even number, but even number, would you be able to write down, Peter, an even number? Any even number in multiples of 2, I like it also. Thank you, Bismarck. Multiples of 2 is good. So multiples of 2, what is a multiple of 2? It will be, how do you write it down? If I ask you, please write me either anyone you want, but if Peter and Bismarck could do it, or anyone else, how do you write them down? 2n, that's good. So it's 2 times n, but what is n in your 2n? You are not telling me enough, right? I don't understand what is your n. N is a whole number. So you see that your set can be written much more efficiently without listing all the elements when it's infinite, by writing 2 times n, where n is a whole number.
All numbers?
Yeah.
Are we sure?
What is your definition of all number, Peter? Just to see that we are, because we are only taking the even number greater than or equal to 2, right?
Yes.
So what is a whole number for you, Peter?
Can I say 1, 2, 3?
I think yes.
And so it is, I think this adequately describes it, right? This is an abstraction of the collection of all even numbers, starting from 2.
Yeah, and Peter said that, yeah, in your definition of all number, you said all number. Okay, they are positive all number. Okay, so you corrected yourself. Okay, good.
Perhaps we can go back to our slides.
But maybe we want to just make sure that everyone understands the concept of pattern, because I think there is like, so a pattern is something which is, so in the first case, I would say the pattern is like something which is repeated itself, but you see, for instance, in whatever is given to you in front of you, you will identify a piece, but if you know that piece, you will know the entire set of picture. So that could be one definition of pattern, I guess. But a pattern in 2 or in the E that we have seen is something a little bit different. Is like you could express the list of number using some kind of formula, in a sense, or some kind of very logical thought. So if you see in 2, you will have 5, 10, 15, and 20, which are multiple of 5. And you could express them very efficiently by saying that there will be 5 times some n, where n is a positive, or what we call a natural number. And you would have all the list writing down without having to write every single element once after the other. So there is kind of a type of formula that link things together. So there is something which efficiently make the next number in terms of the previous one. I would just warn you about patterns, because I see a lot of pattern in Facebook and all social media or things like that. But just be aware that if you have only a finite number of numbers, it could be that you think of a pattern, but you don't have enough information to really know for sure if that's the case or not, because we cannot prove anything with a finite set of number. It could be you could have only access to very specific list and not see what is happening after, and what is happening after is a mess from that point on. So just be careful with that, but you don't go up from conclusion too quickly. But usually when they ask you to find the pattern, they will ask you to do what is the next number. It will be 25, for instance, for 2, or it will be 8 for the E. But just be careful of that.
Maybe if I can add to just tie this back up to our discussion on abstraction. Essentially what we've seen here with patterns is that pattern is the property that we've extracted from, for example, the collection of numbers, right? And then we were able to write down, in our case, for even numbers, a formula that was able to describe it. So we were able to extract the information about how to describe an even number. And so that was an abstraction.
Mm-hmm. Exactly.
And so bringing us back, so this is our picture of a set. And what we're trying to show you here, but yeah, Sophie, you can go ahead.
Go. Sorry.
Okay. So I was saying is that we're trying to essentially communicate to you that a set can consist of anything. We don't just have to always talk about numbers, right? And here we have a set which is a collection of fruit. Yeah. So perhaps our next notion would be the notion of a subset. So if we have the collection of all of the fruit, maybe what I want to do is I only want to end up eating just the banana and the watermelon. So that is me now picking a few elements from the large set. And by picking up a few elements from the large set, the banana and the watermelon, I am now making a smaller collection, aren't I? And so that smaller collection is then called a subset of the original set. Is my understanding correct of that, Sophie?
I believe so.
Okay. But then let's consider another thing. Let's just say we were looking at a set consisting of students in a classroom, right? And all of the students have a pencil case on the table. And so essentially what I want to do is, okay, let me not talk about students in a classroom, but the set consisting of all of the pencil cases. But now I want to make a subset consisting of all the blue pencil cases. What happens if there are no blue pencil cases? Can I make that collection?
Yes, that's what is called the empty set. There is nothing. And the empty set is a subset, the set of nothing. If you think about it, the empty set has a role for set of the same thing like the zero as for number. Like for a very long time, zero was not accepted, but because why would you put a number for nothing? In the same way, it's important for set that you consider the empty set as a set because it's a set of nothing and it also belongs to the sets.
So if I let X be the collection of all of the pencil cases, right? In a classroom, and then I say let A be the collection of blue pencil cases. So if there were no blue pencil cases, how do I denote that?
So it's a bit like a zero, but it's not a zero because it's a set. So they put a bar across to denote it.
Okay, so if there are no blue pencil cases, then A has nothing in it, right?
Mm-hmm.
And you say that I write down a zero with A?
A diagonal bar on it. Yeah.
Okay.
It's like
And
a
so
zero.
So this is empty. Okay. And so this set exists in
Yeah.
our world. Wow.
It's like the zero exists. It's the same kind of idea.
Ah, so it's like zero. Okay. Yeah, I like that. Can you come up with some other examples of subsets? So first you'd have to state your original set and then you describe the subset.
Okay.
Just waiting for some responses in the chat.
Okay. So there is a NACO say this link to the topic probability in math. So
that is true, Nako, because when you study this in school, I think the first place that you actually see sets formally is only in probability. And that's a sad thing though, right? I mean, you could have seen it much earlier. This is actually set theory that we're talking about now, right now, isn't that, Sophie?
yes, it is.
So this is a beautiful area if you want to explore it on your own. Maybe just Google set theory in your free time. Yeah. But yes, Sophie?
Yeah. There is you could do most of the mathematics out of set theory, I guess. You could probably rewrite mathematics in terms of set theory.
So maybe we want to also talk about other types of sets. So we've got subsets, but maybe I neglected something, Sophie, because we've got the collection of all pencil cases and I formed a sub collection. How do I write that down formally, mathematically?
So we would write that A.
Yeah.
It's a little bit like the less or equal sign because it's the same kind of object for sets. but it's
Yeah.
not the same thing because it's round. So it just would say we are not speaking about number here, we are speaking about sets. So we make it a little bit different, but a bit the same, because it's really in your head, it should be telling you that you're speaking to very similar thing. So it's like something included. A is included in X, which would mean that all the elements of A are also element of X, which is exactly what is happening when you take a sub set of something.
I just want to confirm, you can see the whiteboard, right?
I can see it.
Okay.
Everyone can see it, right?
Okay. I'm just double checking that I'm not on the slide because I completely forgot and I was writing, but yeah. Okay, so I think I understand that now. So it's just a bit of a change in notation now that we're working with sets. The objects are sets.
But it's very, it should remind you what is happening with number, because it's very close to the idea. That's why mathematicians choose those very close notation.
Yeah, so here A is the collection of blue pencil cases and X was all of the pencil cases in the classroom, including blue ones. But now in particular, in our example, A has nothing in it. So what it seems here is that this empty set here is now a subset of the big collection. Is that always true?
Yeah, the empty set is always there and it's always a subset. But now Le Bourgain is asking us, well, now he wants an example where the subset is not empty. Would we be able to give him such an example, sorry?
Sure. Okay, but I just wanted to write down that property that whenever you have a set, the empty set, the set consisting of nothing, right? That is always a subset of the original set. But now we were looking for an example of something else. Yeah, let's go back to our picture. Sophie, can you screenshot the original set with fruit?
You want I put it here?
Yeah, you can just put it onto the whiteboard for me.
Okay, we'll do that.
So if we look at that example on the fruit, right? So we had a set consisting of various types of fruit. And now we're looking for a non-empty subset of it. So all I want you to do is pick the fruit that you would like. What would you like to pick? We've also got another example while we're waiting for our picture. So Naku says, okay, there are 10 students that play sports at Serene School. 4 play soccer, 3 play netball, 2 plays both. Can a subset be created out of this example? Okay, that's a good question. Let's investigate. Right, so I've got a set. So this is an example from right. So Nako says 10 students, right? So now I've got a set with 10 students. Right, that's my world that I'm going to live in with 10 students. 4 play soccer, right? So then I've got 4 play soccer. So now in here, I've got soccer. Okay, and the big set is maybe the set of all sports, right? So all sport. Right, and then we've also got another 3 play netball. So I also want to talk about netball. So I'm not sure, maybe for now, let me draw it like this. So this is netball. And we know that 4 play soccer. So I'm going to draw stick figures. That's 1 student. That's student number 2, 3, 4. So I've got 4 students who play soccer. I've got 3 students that play netball. Okay. And then Nako also said in the example 2 play both. Okay, so is this an adequate description? What do you think?
I think it is absolutely. It is a very good description of a set where you create your subset out of some kind of also commonality of what those people have.
But Nako said 2 students play both, and we have a total of 10. I've only drawn 7 so far.
Yes, I might have forgotten those 2 for those. Yeah, there is some which play both as well.
So then maybe my picture needs to be amended, right?
Yeah, I think so. I didn't look at this.
Okay. So, okay. Let's maybe choose a different color. So I'm going to do that. That's for soccer. And then I'm going to use purple for netball. But now I've deliberately done something, and I'm going to include the 2 students that play both. So now I have 6 students play soccer. Oh, there's a problem, right? Is there a problem with our numbers, Nako?
Maybe there is some sport which he decided not to to list, or was it only the sport? A free play both, he said. So it should be free.
3 play netball, 4 play soccer, and 2 plays both.
But he corrected himself now, and he said that instead of 2, it will be 3.
Okay, let me add one more.
Okay.
Okay. So now in total, there are 10 students playing either soccer or netball. And we observe that 6 students play soccer, whilst well, actually 6 students also play netball. But I think this is an adequate depiction of what is actually being described. And now we want to talk about the subsets, right? So we've got the set of all sport. There's obviously some other sports that have not been described in here. Maybe there's swimming, right? And there's something happening in that set. But now if I go all sport, then I think it's correct, Sophie, if I say that therefore the set consisting of all students playing soccer is a subset of the collection of all sport. And similarly, the set of the set of all students playing netball is also a subset of the collection of students playing all sport.
Yes.
But now there's some other properties that I've observed in here. For example, there's a commonality. There's something happening in the middle. In here, this area here.
So this is what we call the intersection of 2 sets. How you denote it. So in math, we want to be very super precise, you see. So you would give name to your sets as usual. You could call, for instance, the student who play soccer like S, and the student which play netball N. And the intersection, you will denote it like with how do you arch down.
So we're going to denote it like that.
Yeah, that's how you denote an intersection.
So then I see that soccer, the set which I've labeled soccer, intersect with netball is actually not empty. Because there's something living in there, so it's not empty. There is an intersection. And we can describe what that intersection is, isn't that so? using our picture. This intersection consists of 3 students.
Mhm.
Yeah, that's quite nice. Are there other properties that we should talk about?
How about the union?
Okay, so is that essentially combining 2 sets?
Yeah, it would be like you take the union of soccer and netball, and you will have the entire set of what of the student which either play soccer or netball or both. So you're considering all that, and the
But then
union like
how do I write this?
you switch your intersection up.
Okay, so then this is going to be like that in a sense.
Mhm.
Okay, let me just write that a bit better because my handwriting was slanted. And so essentially what we're saying, the set which I've labeled soccer, union, the set labeled netball, consists of what? Now I have to draw 10 stick
Mhm.
figures. Okay. Okay, while I draw that, Sophie, maybe you can continue.
So the only thing I would like to say is that probably somehow, in order to draw your sets accurately, you would need to kind of identify your student who play netball with differently than your student who play soccer in order to differentiate them even in the picture and in your set.
I think this is it. Should be correct. 10 stick figures.
Why is it 10 and not 11? I do believe it's like 6 plus
7, 10.
4, which is 10, unless we are making a mistake. But I think it's 6 plus 4, right?
Yeah.
Which is 10, right? Kayla, do you agree? Because we are taking everything which is in the pink circle and the purple circle, but we don't count twice anyone.
So you just count everything that is now being displayed in the combination of the 2 sets. So perhaps what we should also mention is that the intersection is exactly the area that I had shaded in yellow. The union is going to be what I shade in. Okay, it would have been nice to have a highlighter, but let's say green. So the union is everything in here. It is the red set plus the purple set.
I think Tejuden is asking, there are some who are not doing any of the 2 sports, but they would not be in the union of soccer, union netball, because soccer, union netball would only consist on the people who are doing both, either soccer or netball, but not outside. Does it make sense to you?
But we have some other really nice illustrations. Let's perhaps look at that, Sophie.
Okay.
There we go. So again, still talking about fruit, but now we've got 2 subsets that we're looking at. The subset on the left is a collection of all the red fruit from the set, and the subset on the right is a collection of all the yellow fruit. What's happening with the intersection of these 2 sets?
Well, maybe someone can tell us in the chat. What is the intersection of this 2 subsets of the yellow and the red? It's empty. So the zero, obviously, if you write zero, I'm thinking that you write zero because you cannot write the empty set with a bar, because zero would not be the correct symbol to denote the empty set. But to answer also, I just want to answer again, just to make sure that Judin does not have a misperception of a union, because he's saying those doing both should be removed from each sport. But no, in the union, it's not exclusive or, it's either or, and you could also be in both. So you are including every single thing in the union. I hope that makes sense for you. So that's how you define the union. It's either that or that, and this, in saying that, I'm including also those which are in both. So this is a subset of color, yes. So that those subsets are created out of identifying the color of the fruit. So that's how you could think about the subset. And tomorrow there is no intersection, so they all got it, Serene? They understood.
Oh, that's great. And of course, the union, it just means that I'm forming a new subset, which is going to be the collection of all the red fruit plus the yellow fruit.
Yeah, you would have the set of those two. Yeah.
Right. Just trying to move on. So we did already discuss intersection, which is nice. We've seen the illustration of it. But here is another example. Sophie, maybe you can explain this one.
So it would be people who have glasses, and so you can explain, because what could it, not you, but maybe in the chat, what could be how the set is created here? It seems that there is only girls in the left, right? And only boys with glasses in the right. And then you take in one direction, so all the girl, all boy with glasses, and then all people with glasses, I guess. And then you take as an intersection girl which have glasses. That would be how I understand this example, right? So people with glasses, girls, and then intersection, which would be girl with glasses. Does it make sense? So Sigong Fatso is saying that he does not understand intersection, and Paulus is saying that they have long hair as well. But there is one which are like mid-side hair as well. If you see the top one, I think we could argue, I would say, because we don't have probably enough information to say exactly which criteria would the intersection make. So for the intersection, let's see if this example will help you to understand the intersection. But I see that some of your friends are already helping you out, which is very nice of you, I guess. So U is everything, upside down, and the intersection, is it so everything? So the union would be everything that are in both of the set that you are taking the union of, and the intersection will be what is in both sets simultaneously, if that makes sense. So Tendo is say can we say people without glasses as a subset of A, and people with glasses as a subset of B, and then but you see that intersection would not make sense if we did say that. And it seems that we are only girl on the right? So maybe that description, that abstraction, that would not fit exactly this problem, at least to me. So I would say probably what Serene is writing is how I would interpret this problem, as you have the girls and you have people with glasses. And then if you intersect those two sets, you obtain girls which have also glasses. Does this make sense? So the intersection, 3 boys, 3 girls. So I think that it would be that girls don't wear glasses and boys wear glasses. Then there is an intersection of girls who wear glasses. So here you have to see that in this picture, probably the whole set of people is not represented. We have only represented a part of it. We have forgotten probably that boys could not wear glasses here, and we probably should also include that. Okay, but this is an example of intersection as well.
We did also speak about union, and here was a really nice example. So we have the global set. As you can see, here are the bounds for that. Within this, there are 3 sets that I can observe, right? The first one, the first subset is, this is a subset consisting of trees and flowers. And there's a clover leaf as well included. That's the one on the right. The one on the left, well, if we look at the bigger one, this is a set consisting of animals and children. But then contained in that set is a subset consisting only of children. And then this was an illustration for union. Yeah. So, Sophie, do you want to perhaps continue with the explanation here?
So here you have also a notion that comes up, which is quite interesting, is that you would have the very big set which contain everything. And it would be the union of whatever is inside it. So everything you see in this picture is in the big set, in the union of everything you see. But then there is 2 subsets of this big set, which is, if we consider that the children are animals, we can disagree with that. We are part of the animal kingdom, I guess, from biology perspective at least. So you would have 2 different subset here, the vegetal kingdom, which has represented with the tree, the flowers and all, and then the animals and the human being, which are presented on the left, which Paulus say mammals, which could be true. I think they are all, I wouldn't test too much my biology skills because I don't know. Maybe you're better than me for that. And then in the subset, there is a subset of a subset. You see, you can keep going and taking subset of subset of subset of subset and keep doing subset. So here you have an example of a subset of a subset. So here, if I did ask you, for instance, what is the intersection? This is maybe a bit tricky, but what is the intersection of the animals, which we included children, and the children? What would be the intersection of that? Yeah, it is with children. So you see that if you have a subset of a subset and you take the intersection of those 2, what you obtain is the smaller subset, which is included in it. And if you take the intersection of the animal and the vegetal, what would be that intersection? It would be the empty set, right? And the union of the children And the animals will be what?
Mm, just this set, I guess, consisting
It will
of
be, it will be everything in the right, yes. So it would be, yes, everything here.
everything here.
And then the children and the trees.
Children and trees. So you just add the children and the trees together then.
Exactly, and you forget about all the animal. So this is just to reinforce your understanding of what intersection and union is.
That was nice. Perhaps, well, I think we wanted to take a break, Sophie, but we've got some limited time. Should we perhaps start talking about relations now that we have a better understanding about it?
We can. I think we already spoke of relation without mentioning the term relation, in a sense.
It's true. So when we're talking about relation, does this have to only be something related to numbers, or can I talk about a relation amongst any?
Like everything in mathematics, or most of the thing, it might apply to anything, like that could be in your life. But
Okay.
it might be that those relations are more clumsy in the sense that you can formalize them less.
So basically, essentially what I have to do is I have to start off with a set of something, and then I can describe a relation on it. Is that what I'm aiming to do? Well, I guess so.
Yes, that's the case, yes.
And so my set could just be, well, in particular, okay, so I'm using Facebook, and I've got a bunch of Facebook friends. So perhaps my set could be all people in the world, and then the relation that I will now ascribe to the set of all people would be that, well, I know them if and only if we're Facebook friends or something like that.
You can do a relation like that. You could do a relation. We can kind of see what kind of property that relation is.
Okay. Maybe let's look at this one. So what's actually happening here? We've got shapes on one set. And okay, well, firstly, there are two sets. That's what I observe. I've got a set on the left labeled X, and I've got a set on the right labeled Y. The set on the left, which is X, consists of shapes. And the set on the right, which is Y, is only colors. So what's happening here?
I think the relation that we are taking between those two sets, how we relate the one set to the other, is that every shape would have a certain color, and we are associating that.
So the triangle is red. So Sophie, I seem to have lost you. I hope you're still there. So the triangle is red, and therefore it is associated with the red dot on the right. And similarly here, it is the square that is red, and therefore it is associated with the red dot on the right, which is the red from set Y. Likewise, we've got a yellow rectangle on the left on set X, which is now associated with the yellow dot that lives in set Y. So it seems that elements from set X, which was shapes having a specific color, is now being related to elements from set Y, which only consisted of various colors. Yeah.
Yes, I think that's what the relation is doing.
Okay, that's very interesting. Can the students come up with some other relations that they've seen in real life? Do the relations have to take place on different sets, Sophie?
You could relate thing within the same set. So you are kind of still relating the set with itself in a sense, at least abstractly. That's how we think about it.
Okay.
But your relation could be in your set and you relate object in your set. So can you think about some example of relation? We do relation all the time, I guess. Just have to start. You will see once you start, you will find a lot. So one example that we already did without saying, we did a lot. Like for instance, the phone, that was the first thing. And we associated it to a brand. So that was a relation. And then, so they would be related, the two phones, if they have the same brand, for instance.
Let's see.
What did we do? Also for the all living creature that you are speaking in the chat. If you are an animal or vegetal, so you would be related if you are both an animal or if you are both a vegetal. So that's example. But let's see if you can come up with more. Even if I know that 2 hours is a lot to concentrate, but thank you for sticking with us and continuously participating. It's much appreciated.
So we had the set of all cell phones, right? And we say that phone X relates to phone Y if and only if, so maybe we need to discuss what that is. X and Y, phone X and phone Y are the same brand. So in particular, if Sophie and I are both using Huawei cell phones, then we're saying that these two phones are related by virtue of the fact that they are the same brand. Can you come up with some examples?
So there is a one which came up in the chat, Bismarck, which says, he says that we can consider the relationship between advertisement and revenue for a particular company. So
okay. So how? So is one advert related to the other advert if the revenue earned is the same? I don't know.
I think maybe we are in a situation, the same situation we were with pattern, where our understanding of a word relation might be different depending on how we. So I think, not that I can read in your mind, Bismarck, but I would say that you are thinking about a proportional relation where probably there is like some kind of effect on how much advertising you put out, on how much revenue you will come, if I'm correct, which might be a different type of relation that we might be considering here, at least from what I can perceive right now. It might be the same if we kind of widen our mind, maybe. So Bismarck say you are correct. So this might be a different relation than what we are trying to get maybe in here. So relationship of two type of washing machine, if both are Samsung, yes, that's true. It will be very similar to the one from the phone. I know this is a bit so relationship between income and expenses. So this will be also a relationship in terms of how one is a formula of the other. So we could write it as a relation actually, because we could just say that yeah, it would be much more difficult to make it fit into our setting right now out of the blue. But I think it can be done, but it's a different type of relation, but which is proportionally relation. But here we are really trying to create relation more in the concrete sense, where we are looking at a set. So we put our set in a set, and we are trying to relate objects together. So here, Le Bogan say, don't you think it is about the animal and children breathing oxygen and the tree using carbon dioxide? Then that concludes to why it's separated when they are all living creatures. So you see, in our abstraction, we don't always agree, and that's fine. We shouldn't agree on how we abstract, because our own experience will determine, our own knowledge also will determine how we will abstract of things. But it doesn't mean that one is right and one is wrong, because it just means that there was no obvious or very canonical way of separating the sets. And that may be what has been going on the chat about those sets, and it's perfectly fine. There is not one answer in mathematics, and this is very important to recognize that two answers could be very perfectly viable, and as long as it has some logic behind it, and that logic is true. So iPhone is related with a good camera quality. Huawei is related to good storage. So if you are a set of phone which some are iPhone and some are Huawei, and on the other set is good camera quality and good storage, the phone will be related in that way. Okay, that's good, but maybe the attribute that you are giving might be subjective unless we really make them strong, in the sense, what do you mean in good camera quality? It cannot be like up to me, or then your relation will be it's up to my vision of things, and then you can create your own relation like that. So there is a bit that is this image about it is so confusing, a better distinction. Okay, they are still on that image of living creature.
Okay. But maybe we can talk about the one that's on the screen now, right? You can see it. Okay. Because
yes,
I think we can conclude our lesson today perhaps whilst discussing this one.
Okay.
Yeah.
So so in the one which is on the screen, so let's forget about the living creature. It's true, we can probably disagree with how it was classified, and it doesn't mean that any one of us is wrong, but let's concentrate on what is on the screen and see the relation that people have depending on how they connect with social media. So
But I have a question first. Because we seem to be now depicting the relation differently here.
Yeah, here I would say that the set we are considering is the set of people, which actually are in the picture a priori. And then we will say that they are in relation with each other if and only if they are connected through some kind of social media app.
Okay.
At least that's how I understand.
And so we've denoted the people by circles, and then we put a line between the two circles if those two people are connected via social media.
Exactly. So that's how you represent a relation within a set through a graph.
Okay, so if I had to, so that means that this man is related to that man because they're connected via LinkedIn. Is that correct?
Exactly.
But now, the same man is related to this lady because they're connected, I'm assuming, via Facebook.
Yeah.
But now there's a line between this man and that one, but there's also a line between him and her. Does it mean that the first man is connected to that lady?
They are somehow indirectly connected. So via, so it will be about how we define. So they are not directly connected probably with each other, or maybe it depends on how we understand the lines. And there is a lot of things that could be unclear in this picture. But a priori, they might not be directly connected via social media, but they are connected to one person who is connected to the other.
Okay. Okay, so I think the first takeaway is that we now have a different representation of a relation, isn't that so? We represented it using dots or circles and lines between them. That's the first thing.
Yes.
And this, what is this actually called when I use these dots and these lines between them?
That's called the graph. It's a very efficient way to represent relation between sets. And you could completely abstract it and remove the people on top of the dots and remove a square which says which social media, and then just have a bunch of point and line between them and create a graph.
Oh, that is really interesting. Okay. Yeah, so I'm trying to see if maybe I think there's another picture that we can utilize. Yeah, let's talk about this one. Because here is the abstraction, right? But now in a different context. We've now given these people some names, right?
Few of them, but not all of them. So here we are abstracting from the drawing from before, where it was maybe like, you see what happened with abstraction is that the picture becomes less dense and it's more clear in a sense. And but you also like lose that relation, how you relate to the picture in a sense, because you might relate more or understand more the previous picture. But if things get more complicated, the picture like the one we have in front of us is much easier to draw than the one before. So you are abstracting the essential information out of it. Obviously, every picture will need a context, and we would need to explain what are the dots and what are the line between the dots, what do they represent. So it will be a set of people, I guess, and they are connected with each other. It could be like connected by they know each other, or it could be things like that. Anything that you would like to set your relation to be. And then you would draw your people. You forget about their people. You do know that point in the drawing represent people, and then line between them represent some kind of relation between people, like friendship or something that you decide. And then, for instance, you would have Barbie and Ken, which are in a relation with each other. Barbie is also in relation with Dude, and she's in relation with Diva out of intermediate relation. And even with Devon, out of many intermediate relation, if you want.
Because you could go that way, or you could come this way, or you can go through. So there's quite a few like mutual friends. If that was the relationship between the people.
Yes. So if we accept that friend of a friend is a friend, then they are all friends, and that's that extended friendship.
Okay.
If you want.
Well, that's very interesting. So it seems like everybody depicted on this graph, so all of the dots, they are all related to other dots.
No, for instance, yes, they would be related. Yeah, you're right. Sorry. Yes, they are all related to the over dot. It's true.
Yeah. So do we have any questions about such a depiction or representation of relation? So we would like for you to think about this a lot more tonight. Come up with some examples, because tomorrow when we return, you're going to be having a continuation of this discussion with Professor Zurabiana Letsa. And perhaps you can kick off with sharing some of the examples that you had thought about today. So think about relations on a set, and let's get creative, and let's see how we can relate mathematics to everyday life. That is the idea. Yeah.
I'm laughing at the comment in the chat. They have a lot of interpretation of what Barbie and Devon are doing. and that Barbie should be the main character of whatever. But also let's take away that that fact that sometimes things are not as clear as they appear, and it depends on the context, and context matter. And keep that in mind when you speak with people, because they could have their own relation with things that you don't know of, and their own experience with words, and that's how you could even apply your mathematics to your real life, if you wish, what we have learned today in a day-to-day life, very practical way in improving your communication skills. And like the example with living animals, I don't think any one of you were wrong or right. You might be very well all right. And probably the example we have put in front of you didn't have enough information to kind of set a very specific state setting, and that's fine. We don't always have to have the answer or to be right.
I just want to say thank you for all the positive feedback. If this is something that you enjoy participating in, then please let us know, because we will continue with such sessions, and we will be launching a program that you could then all participate in for the rest of the year. But for now, I think, yes, please ensure that you think about some nice examples for the continuation of the discussion tomorrow. I certainly enjoyed the discussion today with Sophie and you all, and we look forward to doing such things again, to spark your curiosity and to have you talking about mathematics and seeing how to relate it to everyday life. Yeah, that's it from me and Sophie. So,
thank you so much.
Yeah. Thank you for joining us, and of course, be back tomorrow at 11. And the session continues from 11 to 1 tomorrow with Professor Zurabiana Letsa. So thank you all. Have a good afternoon, and we'll see you tomorrow.
Bye-bye.